Every night, astronomers scan the sky for possible habitable worlds and extraterrestrial radio signals. So far, no signs of life have been detected. But are all these searches in vain? Are we alone? This is a very important question, because the answer has a lot to do with our place in this vast expanse of space. There is one hypothesis, called the unique Earth hypothesis, that says we shouldn't look for life in other stars. But is this hypothesis correct? We'll start with the broader concepts, then focus on the hypothesis itself, and then look at recent discoveries to see if they fit. Here is our proposed plan. We haven't talked about this kind of theory on our channel yet. We cover a lot of different topics, so what comes next will be particularly interesting. You've probably heard the term habitable zone around a star. Well, the place where exoplanets are at a suitable distance for the origin of life, where it's not too hot but not too cold either, is also called the Goldilocks Zone. But did you know that a galaxy also has its own habitable zone? And not all galaxies are habitable. The further a star is from the galactic nucleus, the lower its metallicity, i.e., the lower the amount of elements heavier than helium. This decrease is due to the formation of heavy elements in the cores of giant stars and supernovae. Such stars are concentrated in much higher concentrations near the galactic core because there is enough material there for them to form, which means that the most distant stars in the galaxy lack the ingredients for life. A supermassive black hole is usually at the center of a galaxy. It can emit huge amounts of X-rays and gamma rays. All nearby exoplanets are constantly exposed to this deadly radiation. Life could never thrive in such conditions. Our galaxy is of the spiral type, with dense arms extending to the edges. Such arms also become destructive to life. Here, stars regularly pass close to each other and disrupt the orbits of exoplanets. Imagine if Earth suddenly entered Mercury's orbit. In addition, these regions also have the problem of nearby supernovae. As supermassive black holes, they regularly emit deadly radiation. NJ indicates that the habitable zone of Zalax is a place close enough to the center of the galaxy with enough complex elements, but far enough away from the core and arms to avoid gravitational disturbances and radiation overdose. We are still in the early stages of understanding what part of the galaxy is habitable. For the Milky Way, all of these factors would make most stars unsuitable for life. The remaining stars must be of the right type and planetary structure for life. We used to think that every star had a habitable zone, the theoretical distance at which liquid water could exist. However, this is a very simplistic viewpoint that does not take into account the spectrum or habitability of stars. For example, low-mass stars emit much less visible and infrared light than main-sequence stars, but they can emit huge amounts of X-rays and gamma rays. This means that their habitable zone may contain water, but the levels of X-ray and gamma rays are so high that the complex molecules might just break apart, killing any possibility of life. The deviation of light from our Sun is very small, less than 0.1%, but for other stars, it can vary by up to 500%. As a result, the boundaries of the habitable zone move throughout the system as stars get darker and brighter. This means that worlds become habitable and escape, which in turn kills all possible life. But even if we find the right stars, it's not at all certain that the planet will be suitable for life. We also need the planets to be properly aligned. The configuration of our system is as follows. Rocky planets are close to the star, while gas giants are farther away. Rare in other star systems. Most only have rocky worlds or gas giants near stars known as hot Jupiters. But in our case, it was this unique setup that helped give birth to life. There is a direct correlation between the number of planets in a star system and their circular orbits. Systems with only 1 or 2 exoplanets tend to have highly elliptical orbits, meaning that an exoplanet can go in and out of the star's habitable zone during the course of a year, again destroying life. However, systems with increasingly large exoplanets have orbital resonances. This creates much more circular and stable orbits, so an exoplanet can remain in the habitable zone all year round. Orbital resonance is too complicated, but the point is that such a system is balanced and keeps each planet where it should be. And as the Earth begins to approach the Sun, orbital resonances pull it back, and vice versa. But even if we get orbital resonances, rocky inner worlds, and outer gaseous exoplanets, the likelihood of finding life there is slim. Models of the early solar system show that Jupiter was crucial to the origin and development of life on our planet. Jupiter has orbital resonance with every asteroid in the asteroid belt, keeping them between itself and Mars. Because of this effect, asteroids will constantly bombard the Earth, and life cannot thrive. Why, if there were no Jupiter, life would be unlikely to have started. At the dawn of the solar system, it actually drifted into the interior of the solar system and threatened to destroy the inner planets. But Jupiter has a unique resonance with Saturn, and Saturn with Uranus, and so on. This resonance meant that Saturn pulled Jupiter out of its inner spiral, preventing a collision with Earth and Mars. Consequently, for life to arise on an exoplanet like Earth, we need, among other things, a unique planetary arrangement. But that's not enough. It also requires the right type of planet and satellites to become habitable. First, the size of the planet requires the right gravity, or it can be very unfriendly. If there is too much light, the atmosphere and liquid water can simply escape into space. This is exactly what happened with Mars. Also, the planet's atmosphere must have the right composition, or it will be uninhabitable, like Venus. Its atmosphere has a high concentration of carbon dioxide, making it the hottest planet in the solar system, even though it is in the habitable zone. The geologic forces created by plate tectonics, mountains, volcanoes, earthquakes, and deep-sea trenches are crucial for life. First, we believe that life had to have originated around hydrothermal vents caused by tectonics, so it could not have existed without them. And secondly, tectonics is very important for complex life, but more on that later. Tectonics occurs when molten rock mixes with the Earth's core. This iron-rich magma rises to the surface and helps create Earth's magnetic field. The field that protects the planet from the solar wind and is an important shield not only for organisms but also for the atmosphere. Without a magnetic field, as we know, the Earth would quickly become uninhabitable. Our tectonics is aided by the radioactive decay of the planet's core, internal heat, and suddenly, the Moon. Our month is unusual. It is by far the largest moon for its planetary size, with a mass of 27% of Earth's mass. This means that its gravitational pull on the Earth is enormous. This creates tidal friction and heats the planet's mantle. And without a massive moon, we may not have vital tectonics. But the moon does something else. It stabilizes its axial tilt. The Earth, as we know it, rotates at a slight tilt, which is why we have seasons. The moon's tidal forces keep its tilt constant and stable. You can see how many shades there are. Suppose we found an exoplanet with the right planetary structure, the right size, the right composition, plate tectonics, and a large exoluna around the right stars in the habitable zone of the galaxy. Will there be life? Probably, yes, we do. Scientists are currently studying Mars to see if life existed on it billions of years ago when it had oceans, plate tectonics, and a dense atmosphere. If evidence is found, there is almost certainly life on these distant worlds. But it's important to realize, not complex life, but simple life. More than bacteria. Complex life, such as multicellular or intelligent life, requires special conditions. In fact, life has existed on Earth for at least 3.5 billion years, but truly complex multicellular life first appeared only 540 million years ago. For 3 billion years, only the simplest organisms lived on Earth. Little by little, much more complex structures began to evolve. But it is still very far from animals and plants now. These early multicellular organisms resembled an amoeba and consisted only of mountain cells. But you know what's amazing? This cooperation of cells seems a complete coincidence. The probability of this event happening again is negligible, as it took 800 million years. There is a high probability that multicellular life is pure chance. But that's still not hard life. It took a natural revolution to create our complex ecosystems. It happened about 541 million years ago in the Cambrian explosion. Imagine that the Ice Age has just ended. The Earth is gradually warming. Glaciers are flowing down from mountainous regions, releasing massive amounts of nutrients into the oceans. Algal blooms are in full bloom, and the atmosphere is filled with oxygen. Those nutrient-rich mountain ranges only came about because of tectonics, so the Cambrian explosion could not have happened without it. Thus, tectonics seems crucial to complex life. The abundance of nutrients and oxygen meant that organisms could afford to burn energy and move elsewhere to feed. Some then evolved to prey on other species. In a few million years, life evolved from very simple sponge vacuoles to crustaceans, squids, vertebrates, and sea stars. We talk about life all the time, but understand, we can't call these Cambrian creatures intelligent. Do you know what I mean? To summarize, what does a planet need for life to exist? A planet has to be in a habitable part of the galaxy, have the right type of star, the right type of orbit, the right type of planetary neighbors, the right size, the right composition, the right tectonics, a large moon, and a natural disaster that results in multicellular life. There are so many factors. It turns out that Earth is incredibly unique, and the odds of finding a duplicate are vanishingly small. Or maybe we're looking at it wrong. In recent years, this hypothesis has run into a out-of-nowhere kind of problem. Some satellites of Jupiter and Saturn have liquid water beneath the surface and probably have hydrothermal vents. Here's how they can hide life. This has led some scientists to question the unique Earth hypothesis. If we detect life on distant ocean moons, it should be so simple that this hypothesis will have to be rejected because we have a new model for colonizing a planet, or rather, a satellite. In addition, there are many Jupiter-type planets in the galaxy. And since both of our gas giants, Jupiter and Saturn, have oceanic satellites, I'm referring mainly to Enceladus and Europa, we can expect that there are many fully habitable exolunes. We may never find a twin Earth, but there seems to be a strong possibility that somewhere in space we may find worlds and other life even more alien than our own. It is no secret that at the center of the Earth is a very hot core. Did you know that it is getting colder slowly but surely? What happens when that happens? Simply put, it's becoming. And to be a little more specific, the planet's rotation is slowing down, which is significantly reshaping the Earth's crust. But that's not a bad thing. Convection currents in the mantle disappear, which means the planetary dynamo disappears. The Earth loses its magnetic field and becomes completely defenseless against cosmic radiation that destroys all life on the surface. This bleak picture ends with the solar wind blowing smoothly from Earth into the atmosphere and changing the view of our planet Mars. All in all, the outlook is not bright. But our goal is not to scare you about the end of the world. We're talking about something else. We talk about the interior of our Earth because few people know that it also has an outer core and is in a liquid state. How do we know this? After watching this video, you are probably even more afraid of earthquakes. Anyway, as always, it's going to be interesting. So for now, let's head out into space to look at our home planet. Looking at this insanely beautiful little ball, we see that it is about 70% covered in water. There's no secret. In fact, all oceans are simply floating on top of giant layers of argillite that mankind once decided to call land for some reason. In fact, the concept of buoyancy, where lower density objects rise above higher density objects and the latter sink accordingly, can explain processes on a much larger scale than the existence of oceans. Similarly, we can explain why ice, a solid, can float on top of liquid water, why helium-filled balloons float in the atmosphere, and why rocks sink when we throw them in a pond. The latter simply requires a different way of looking at things. Rocks don't sink, and the water, which is less dense, rises around the rock, and this same principle of buoyancy explains the layered structure of our planet. In fact, the rarefied atmosphere of all layers of our planet's crust floats only on the liquid ocean, which in turn crawls over the crust, moving through the even denser mantle. The mantle is ultimately unable to descend to its lowest and densest point, the core. Ideally, the most stable state the Earth could be in would be layered like an onion. The densest elements would be closer to the center, and each outer layer would consist of progressively less dense elements. In fact, each earthquake is a sign that the planet has come one step closer to its ideal, because after each earthquake, the speed of its rotation, although insignificant, but still increases. This is exactly how our world, and other planets as well, are organized. All that remains is to remember where all these elements come from. Long ago, there was almost nothing in the universe except hydrogen and helium. The heavier elements were created by the stars and returned to the universe after their deaths to form the next generation of celestial bodies. But for Saros, a whole cocktail of new elements was born. Nitrogen, silicon, magnesium, carbon, oxygen, sulfur, and iron were added. And around almost all of them, new stars and protoplanetary disks begin to form. The external pressure of a newly forming star basically pushed the lighter elements to the outer parts of the future star system, and gravity caused its unstable disk to collapse and soon to form planets. Speaking of the solar system, the 4 densest planets by far are in its interior. All of them could not gravitationally hold the large amounts of hydrogen and helium from which they were formed, so they did not become gas giants. But the outer planets, which were more massive and farther away from the Sun and therefore received less radiation, were able to retain large amounts of these ultralight elements and form gas giants. Earth and other worlds are similar in structure. The densest elements concentrate in the core, while the lighter elements form the less dense layers surrounding them. Not surprisingly, the heaviest and most stable element in the Earth's core, iron, has become the most abundant element, and huge masses of it are formed by supernovae. But not everyone knows that between the solid core and the mantle is a 2,000-kilometer-long layer of liquid called the outer core. Our planet has a liquid layer that makes up 30% of its total mass. We have only been told about this by scary soothsayers, seismic waves caused by earthquakes. There are 2 types of seismic waves during an earthquake. A pi wave, also known as a primary pressure wave, is a type of pulse on a stressed surface. The E wave, also known as the secondary transverse wave. Its journey is like the movement of a wave across the surface of the sea. Both waves travel outward from the point of origin, spreading their vibratory effects not only over the surface near their epicenter, but also around the world. Therefore, seismic monitoring stations analyze both types of waves. However, S waves do not propagate through a fluid, unlike P waves, which not only can travel straight through a fluid, but can also be refracted. As a result, we know that the Earth has a liquid outer core, a solid mantle on the outside, and a solid core on the inside. This is why the heaviest and densest elements are in the core of the planet. But why is the outer core in a liquid state? All the elements we know, and with them iron, are the same in many forms, depending not only on pressure but also on temperature. The problem is that iron is much more complex than most of the elements we know. It is capable of various crystalline solid forms, But today we are not at all interested in talking about normal pressure. No, we're going to the Earth's core, where the pressure is hundreds of times higher than water pressure and millions of times higher than atmospheric pressure. But first, it's important to realize that the atmosphere has a density of about 0.001 gigapascals, and the inner core has a density of about 330-360 gigapascals. 330 gigapascals requires simply amazing temperatures comparable to the surface temperature of the Sun, which, I remind you, makes it possible to melt iron. However, at the same temperatures but lower pressure, iron easily remains liquid and solidifies as the pressure increases. How does it threaten the Earth's core? The highest temperature at the center of the Earth is just below 6,000 Kelvin, the same level at which the melting point of iron at the boundary between the inner and outer core is also at, according to recent estimates. Our dear Earth is gradually cooling down. It radiates heat into space faster than it produces heat itself through radioactive decay. Inside the Earth, the internal temperature drops, but the pressure remains constant. In other words, our home planet was still this warm creature waiting to be born. Its temperature was much higher than it is now. Perhaps the entire core was once liquid, and now that it is cooling, the inner core continues to grow. The final stage is complete cooling and the formation of a giant lump of iron inside our planet. The density of solid iron and its sheer mass causes our planet to shrink, which is why we get just a huge number of earthquakes. To summarize, the fluidity of the core is due to its temperature, which allows the iron to melt, though only where the pressure is reduced. And the Earth is getting older and colder. More and more areas of the core solidify, and because of this, our beautiful planet is constantly shrinking, albeit very slowly. If you want to know what this looks like, take a look at present-day Mercury. Here, you can see the same huge edges of the largest ones. Mercury itself took a long time to cool down and shrank very hard, causing giant cracks of tens or even hundreds of kilometers to appear there. We just need to remember that every earthquake is a wake-up call. That means only one thing. Earth is a little closer to finally cooling and solidifying. If you were offered to visit any part of the solar system, where would you go? Perhaps you would choose the inner part where our rocky planets Mars, Venus, Mercury are located. Or maybe you want to go outside and look at Saturn, Jupiter, or Uranus. Or you can travel beyond the orbit of Neptune to see Pluto and Poscope. We suggest you go to the part of the solar system where Mars's mansions have ended, but Jupiter's dominion has not yet begun. Straight to the Asteroid Belt. This mysterious place contains many marvelous objects that can tell us a lot of interesting things. This is where NASA plans to send its new spacecraft to study one of its inhabitants in detail, Asteroid Psycho 16. This subject is special. It's been called the savior of mankind. The asteroid belt is often referred to as the main asteroid belt or simply the main belt, thus emphasizing its difference from other similar areas of small planet clusters, such as the Kuiper belt and the cluster of scattered disk objects or the Oort cloud. The total mass of the main belt is equal to about 4% of the Moon's mass, with more than half concentrated in the four largest objects: Ceres, Pallida, Vesta, and Hygeia. Ceres is the largest and only dwarf planet in the main belt, measuring more than 950 kilometers in diameter and twice the combined mass of Pallida and Vesta. But most asteroids, of which there are several million, are much smaller, down to a few tens of meters. In addition, asteroids are so widespread in this region of space that they have not harmed any spacecraft passing through the region. In the 19th century, it was widely hypothesized that the asteroid belt represented the remains of the erstwhile planet Phaethon, which was destroyed in a collision with a large object millions of years ago. Then we attended these events and even hosted them. This is a joke, of course, but we actually have this video, and if you haven't seen it, you can watch it. At the same time, you can compare how much our channel has changed in a few years. As for the Phaethon hypothesis itself, it was soon firmly rejected, one of the most important arguments being the total low mass of the belt. But then how did the belt form? The main theory now is that it started forming right near Jupiter, whose gravitational field was constantly introducing serious perturbations to the orbits of planetesimals. The excess orbital energy received from Jupiter caused these bodies to collide more violently with each other, preventing them from being blindsided by the protoplanet and further enlarging it. As a result, most of the planetesimals were fragmented into numerous small fragments, most of which were either ejected outside the solar system, which explains the low density of the asteroid belt, or moved into elongated orbits on which they, getting into the inner region of the solar system, collided with the planets of the Earth group. Collisions between asteroids occurred after this period, which led to the appearance of numerous asteroid families, groups of bodies with similar orbits and chemical composition, which includes a significant number of existing today asteroids, as well as the formation of fine cosmic dust that forms the zodiacal light. In addition to this, Jupiter's gravity also creates regions of unstable orbits where asteroids are virtually absent due to resonances with Jupiter. An asteroid getting there in a relatively short time would be ejected from that orbit outside the solar system, or would join the population of asteroids crossing the orbits of the inner planets. Now, there are almost no asteroids in such areas, but the orbits of many small asteroids continue to slowly change under the influence of other factors. There is also a version that the asteroid belt was formed as a set of byproducts in the formation of the planets of the solar system. In other words, asteroids formed as debris from the formation of other planets, which were then dropped into the region between Mars and Jupiter, where they are today. The most important distinguishing feature of individual asteroids is their spectrum, by which we can judge the chemical composition of a particular body. There are three main spectral classes of asteroids in the main belt. Attention on the screen: carbon, silicate, and metal, or iron. All of these classes of asteroids, especially metallic asteroids, are interesting from the point of view of the space industry and especially industrial asteroid exploration. Asteroid Psyche 16 belongs to the iron class. Its shape is similar to a potato, only it is very large, with a diameter of about 226 kilometers and dimensions of 279 x 232 x 189 kilometers. Psyche orbits the Sun at a distance of 2.53.3 astronomical units. Recall that 1 astronomical unit is the distance between the Earth and the Sun. Psyche takes about 5 Earth years to make 1 revolution around a star, and it takes just over 4 hours to make 1 revolution around its axis. Today is Psyche's day, mostly made up of 90% iron, nickel, and other metals, very similar to the core of a planet. It has even been suggested that Psyche is the high metal core of an ancient protoplanet that may have been destroyed by collisions with other asteroids before it could complete the process of becoming a full-fledged planet. An interesting asteroid is the primary target of the Psyche mission. According to already announced plans, the U.S. Space Agency will send its equipment there in 2022. The main goal of the mission is to find out if Psyche is indeed the core of a planet-sized object and to learn more about the formation of the solar system. But is that the main goal? Or maybe NASA is being a little silly? The fact is that in the media there was information that simply stirred up the public. They report that in addition to nickel and iron, the psychic rocks also contain platinum and gold. Some experts have even calculated the total cost and came up with an impressive sum of $700 quintillion. And according to the space treaty drawn up by the United Nations, space is not a matter of national property, but belongs to all of humanity. It turns out that this money is enough to eradicate poverty on Earth forever, because each of us is entitled to about $2 billion. It became a harsh name like Savior of Mankind. But before you start planning what to spend your rightful $2 billion on, I'm going to quickly disappoint you. There is no gold and platinum for the Psyche, even in such quantities. It's a complete fabrication. But so popular that even NASA had to step in to assuage the gullible minds of the dubious article. The organization officially denied any suggestion of gold reserves, stating that Psyche 16 is not made up of gold, but iron and nickel. NASA also claimed that even if Psyche 16 was full of gold, the cost of mining would be too high, and therefore the profit would be zero. But of course, this NASA claim can be refuted. They say they are deliberately not hiding the duty to destroy everything under them. But let's think about this. No satellite spectrometer can detect gold. It can only be determined by some circumstantial evidence. Furthermore, it is not known exactly how gold is normally formed today. Just theories. How is it suddenly known that the Psyche has reserves and so many? It is believed that gold is formed during the explosion or collapse of a supernova due to the collapse of neutron stars. According to this theory, after an explosion, metal and metal-containing dust, including heavy metals such as gold, are ejected into space where they later condense. That's exactly what happened in the solar system. And since the Earth was in a molten state right after birth, almost all the gold on Earth is in the core. The logic here is probably this. Since Psyche is thought to be the core of an amorphous planet, this means that it, like Earth, is full of gold. That's about it. Of course, our solar system is rich in mineral resources, and there are indeed many resources that can be turned into money. The entire space market is already worth hundreds of billions. More and more people are talking about it, including us here on the channel. We made a video about it. And it is inevitable that development of these resources will begin in the near future. And while some companies believe that asteroid mining is the most promising industry in space, such as NASA's Psyche asteroid mission, in reality, it is probably purely scientific in nature and aimed at studying the formation of the solar system.